In this slidecast, we'll discuss shell sort. Shell sort is a better insertion sort. It is a kind of insertion sort, but it has some better performance than the quadratic sorts. It's named after its discoverer. A shell sort can be thought of as a divide and conquer approach to insertion sort. So instead of sorting the entire array, shell sort sorts many smaller subarrays using insertion sort before sorting the entire array. So here's a trace of shell sort. We set a gap value equal to 7, and that will signify the subarray 1, where there's a space of 7 between each element in this subarray. And here's subarray 3, 4, so we can identify all of the subarrays that have a gap of 7. And the first thing we do is sort subarray 1. That's sorted. Then we sort subarray 2. It's in order. Subarray 3 is in order. Subarray 4 is in order. Here for subarray 5 we need to swap. We also swap for 6. We swap again. What we're doing is just getting each subarray in order. And here's subarray 1. It's in order. And here's subarray 2. It's also in order. So now all of the subarrays with a gap of 7 are sorted. Then we sort on a smaller gap. So a gap value of 3. Here's subarray 1. Here's 2. We need to sort those. Here's subarray 3. We order those. Here's subarray 1. We need to swap those values. Here's subarray 2. It's in order. 3. We need to swap the final two values. Now here's subarray 1. It's in order. Subarray 2. It's also in order. Subarray 3. We need to swap the final two values. Here's another case for subarray 1. It's in order. Subarray 2, we need to swap the final two values. Subarray 3, nearly sorted. Now we're back to subarray 1. We need to bring the 65 much earlier. And now all the subarrays with a gap value of 3 are sorted. Then we sort on a gap value of 1, just using the regular insertion sort. And now remember, we take one element at a time and then we insert each new value into its proper place in the sorted subarray. 45 is where it belongs. 62 is okay. Now 35 goes as the second element. 55 would be second to the last. 65 is okay. 57 goes right after 55. 60 goes right before 62. And so forth. 75 is okay. 70 we need to insert. 75 is fine. 90 is at its proper place. 85 needs to go second to the last. 80 needs to go before 85. And finally 90 is in sorted order. So here's the shell sort algorithm. We set the initial value of gap to be n over 2. And while the gap's greater than 0, for each array element from position gap to the last element, we insert this element where it belongs. And if gap is 2, we set it to 1. Otherwise, we set the gap equal to gap divided by 2.2. And that just experimentally was shown to be, a good choice. Now the refinement of step 4, we can have a next pause as an iterator to the element to insert. We save the value of the element to insert in next val, and while next pause is greater than first plus gap, and the element at next pause minus gap is greater than next value, we shift the element at next pause minus gap to position next pause, and we decrement next pause by gap. Then we finally insert next val at next position. So this is just the part of the insertion sort where we're determining where to insert that value. Remember the analogy of the card players where you have a sorted deck of cards in your hand, and insertion sort is like picking up a new card and inserting it in its proper position. Now, because the behavior of insertion sort is closer to order n than order n squared when the array is nearly sorted, this pre-sorting speeds up later sorting. So this is critical when sorting large arrays where the order n squared performance becomes significant. The ideas with these gaps is we can very quickly get items that are way out of order and push them closer to where they need to be in the final sorted array. Now, a general analysis of shell sort is an open research problem. The performance depends on how the decreasing sequence of values for gap is chosen. So if successive powers of 2 are used for gap, the performance is order n squared, and if successive values for gap are based on Hibbard's sequence, then it can be proven that the performance is order n to the 3/2. And other sequences give similar or better performance. So shell sort is something that's been studied quite a lot in the research literature. Now, our algorithm selects the initial value of gap as n over 2 and divides it by 2.2 and truncates the result. And experimental studies show that the performance is about order n to the 5/4 or even order n to the 7/6, but there's no theoretical basis for that. That's just by observation. You can hear my cat meowing in the background here. All right, here's some code for shell sort, and I'd like you to pause and look at this on your own and see how the code matches what we've learned. And that brings us to the end of this slidecast.